So vectors are quantities with both direction and magnitude. Let's say you have the movement of a ball and it travels through the air like this. Well, vectors are graphically represented by arrows, so look like this. The length is decided by the magnitude, and the direction, so where they point, is decided by the direction, which is usually an angle or a compass bearing like northeast. Now when we write vectors, the symbol is going to be an arrow. Now you can add vectors in multiple ways. First way is graphically. Graphically adding vectors, however, has a problem. It's not sufficiently accurate. For example, let's say you have two vectors here and you want to add them graphically. Well, you could use the parallelogram method, which looks something like this, and you'll get your result. These methods are cool, but I'm not going to teach them. They're good for visualizing and checking your math, but the most powerful, precise way is adding by components. Adding vectors by components basically means you add the x part and the y part, because every vector has its x part, his x component, and his y component. Well, let's see this concept in action. So let's take a vector, and we're going to call this vector v. Vector v is broken down into two components. We have the y part, so we'll call this v with a little y, and the x part, which we'll call vx. You can imagine this as a right angle triangle, which means that to find this vector's magnitude and direction, we can use trigonometry. Now let's do some quick equation deriving. To find the y component, we can use sine, because remember sine is opposite, so opposite this angle, and divided by the hypotenuse. So opposite over hypotenuse is vy over v. Oh, sorry, I forgot to write the angle. Now if you multiply both sides by v, then you get vy is equal to v sine. This is the formula for the y component. If you go and do the same thing with the x component and use cosine, because remember adjacent over hypotenuse. If you go and do it with cosine, you get vx equals v cosine. So these are the formulas for the magnitude of the x and y components of vector v. Now how about the magnitude of v itself? You can use Pythagoras because it's a right angle triangle. That means v2 is equal to vx2 plus vy2. In this video, to solve problems, I'm going to be writing it as v equals root vx2 plus vy2, which just skips a step and it makes it a little easier. And I want these videos to be efficient for you while also not skipping too many steps. Now how about finding the direction, which is the angle? The direction can be found with tangent. So let me make some space up here. The direction is tangent equals vy over vx. And the reason why this is because if you remember from trigonometry, tangent is also equal to sine over cosine. And sine is the y coordinate, cosine is the x coordinate. Now again, I'm going to simplify this formula a little bit. Instead of writing all this, I'm going to be writing it as the angle is equal to tan minus 1. So the inverse of tan times vy over vx. Same thing. I highly recommend you write these formulas down somewhere in your book. We're going to be using them today. Here we have two vectors. So this one we'll call v1 and this one we'll call v2. When you add them up, the resultant vector looks like this. Because you just have to connect the tail of the first one to the tip of the last one. And we'll label the resultant vector as vr. Now this resultant vector, what if you wanted to find the components of it? Now here's an important thing. The sum of all x components equals the x component of the resultant. So the x component for this red vector, which we'll call vrx, is the sum of all x components. So that would be the x components of vector 1 plus the x components of vector 2. Same with y. So all the y components equals the y component of the resultant vector. So let's use that. This is the x component and the y component of vector 1. This is the x component and the y component of vector 2. This is the y and x components of vector resultant. That means this vector here plus this vector here equals the length of this vector here. Same with the y. This one here plus this one here equals the length of this one here. And then once you find those values, you can go ahead and use Pythagoras to find the magnitude of the resultant vector itself. That's the basic concept behind adding by components. It's very precise and you're going to be using it a lot in 2D kinematics. And here's a rule to remember. Do not add x to y. Do not add them together. Add y to y and add x to x. Here's our first example problem for today. So you have a hiker and he goes on a journey. He travels 5 kilometers east. And then he decides to travel 12 kilometers at 30 degrees north of east. Let's break this down. So first let's resolve each vector into its components. This value we'll call v1 and this value we'll call v2. v1 has these two components. The x is 5 kilometers east. And it doesn't say he goes up or anything, so the y is just 0. Now v2 is a little bit more tricky. If you remember the formulas for finding the x and y components with trigonometry, that's what we're going to have to use. So it gives us 12 kilometers as the magnitude for this vector. The x component, if you remember, is equal to 12 times cosine 30. 12 is the magnitude of the resultant vector, which is where we got 12 from. And then cosine 30 was cosine of the angle. Same with y. Y is equal to 12 sine 30. Now we just have to add up all the x's and all the y's. Now let's start with the x values. So x1 plus x2, when you put it into a calculator, you get 15.39 kilometers. Now y1 plus y2, these two guys, is equal to 6 kilometers. We can go ahead and use Pythagoras, but I want to show you what this looks like on a graph, because in a test, you might be asked to graph out vectors as well. Now 5 kilometers east, that can be like this. And then 12 kilometers, 30 degrees north of east. What does that mean? North of east means you start going north and then you tilt 30 degrees to the east. So it looks something like that. And the 30 degrees would be here. The resultant vector, it goes from the tail of the first vector to the tip of the last vector. So the tail of the first vector to the tip of the last vector. Looks like that. And remember, we're adding these y components up and these x components to find this and this, 6 and 15. If you went ahead and used Pythagoras, you would find that the magnitude of this vector here is roughly 16.52 kilometers. Now how about the direction, this mystery angle here? Now if you remember, you can use the inverse of tangent to find the direction. So tan -1 of y over x. So y is 6 divided by x, 15.39. Put this into a calculator, you get roughly 21.3 degrees north of east. There's our two values for this vector, the direction and the magnitude. There we go. Let's go through a bit of a harder example. This one has 3 parts, so it's got 3 vectors going on, not just 2 like the previous one. Imagine a fighter jet on a recon mission. And first, he moves 800 kilometers north. And then let's say he gets spotted and he has to escape. So then he goes 600 kilometers, 35 degrees east of north. Then lastly, he has to return back to base. He travels 900 kilometers at 50 degrees south of east. This is his 3 movement paths. Now before we go through this together, I want you to try and solve this yourself. It's going to take a bit of thinking, but give it a go. Now let's go through this together. So break down the vectors into components. Let's do that first. Now the first vector, we're going to call him D1 for displacement 1. This one we'll call D2 and this one will be D3. Now D1, the X component is 0 and the Y component is 800 because what we're going to use is just north going up as Y and X can be east and west. That's our frame of reference. Next, D2 has an X component of 600 cosine 35 and a Y component of 600 sine 35. Finally, D3. D3 has an X component of 900 cosine 50 and the Y component is 900 sine 50. There's all our components and we just have to add it all together. But we can't forget this. This Y here is going to be negative because he's traveling south. Now we're ready. We just have to add all of these X's and Y's together. So all the X's, if you put it into a calculator, 1070.1 kilometers. So that's his X vector. How about Y? Well, when you add all the Y together, you get 454.4 kilometers. If you went and graphed this out, which is optional, but I like to do it to visualize whatever's going on, it will look something like this. So he travels 800 north, then he travels 600 kilometers east of north. So that would mean east and then you tilt up to north. So 600 kilometers. And then south of east, 900 kilometers, which will look like that. And the resultant one we're looking for is this. And we'll give him a name dr for resultant. So here's the X component of dr. And here's the Y component of dr. With this information now, we can go and use Pythagoras. So dr is equal to root drx plus root dry, all of it squared. Go and plug in your values and you get roughly 1162.2 kilometers. The direction, remember we just used tangent. So the Y over X, which is 450 over 1000. And this is roughly equal to 23.1 degrees northeast. So there we go, direction and magnitude. Now we've just gone through some very heavy addition stuff. So we're going to move on to subtraction and multiplication now. Subtraction and multiplication are very, very simple compared to addition. Now let me make something clear. No vector is ever negative in the sense of its magnitude. It's always positive in terms of magnitude. Rather, negative shows the direction. So let's say you have a vector v. The negative version of this vector, it would have the same length, so the same magnitude, but it would be going the other way. So same length, opposite direction. Multiplication is even more simple. Vectors can be multiplied by what's called a scalar, and we're going to call it c. So c times v is a vector with the same direction as magnitude v. The only thing that changes is the magnitude. So let's take vector v1 again. Let's say it looks like that. Vector v2, which is 1.5 times v1, would look 1.5 times longer, but in the same direction. What if you multiply it by a negative number? Multiplying it by a negative number changes the magnitude and then flips the direction. So let's take a third vector. And this vector is equal to negative 2 times vector 1. This one would look like vector 1 here, but flipped and 2 times longer. Hello, today I'll give you an introduction on projectile motion. If you remember 1D kinematics, it was all linear stuff, so a ball falling down or a car moving along a straight line. 2D kinematics and projectile motion deals with stuff like golf balls or bullets and thrown objects, and they can follow a path in 2 dimensions, horizontally and vertically. Let me explain to you how Galileo was the first person to understand projectile motion accurately. Let's imagine an example. Let's take a drone. And the drone is flying through a field, and the power, it's lost and it crashes. And it's represented like this. Each of these points can be represented with vectors. So as the drone crashes toward the ground, we can predict its motion accurately by breaking up the vectors into two parts, x and y. So the x component and the y component. X component, y component, x component, y component. As you can see, it's dropping faster and faster. And once you've considered the x and y components separately, you can apply the kinematic equations to predict exactly where it would fall. Now here's some details about this motion here. At t equals 0, the drone only has a horizontal component. It's not moving down at all. But once its power is lost, acceleration due to gravity takes place and it starts dropping bigger and bigger. Now in this video, we're going to assume that the horizontal acceleration is always constant. And we're also neglecting air resistance, which is normal. So in summary, the horizontal speed is unchanging and the y speed gets faster and faster because of acceleration due to gravity. What did Galileo discover? Well, now in the next video, I'll teach you how to solve projectile motion problems. In this video, I'll teach you how to solve projectile motion problems and the approach you should take. So, first problem, you kick a soccer ball off the ground with an initial velocity of 20 meters per second, and it's kicked 30 degrees relative to the ground. The only force acting on the ball is gravity, and we're going to ignore air resistance. How do you find the max height the ball will reach? Let's start with the diagram. At the start, it gets kicked up at 30 degrees, 20 meters per second. And then it's going to fly through the air, like this. Obviously, these will all have their own vectors. Of course, we also have the acceleration being gravity. Okay, step 1, we're going to resolve the initial velocity into its components. So the y component and the x component. His x component, so the horizontal velocity initially, is given by 20 times cosine 30, which is roughly 17.32 meters per second. And if you're a bit confused, this is the initial velocity, 20 meters per second. And this is the angle at which it was kicked up at. Same with the initial vertical velocity, but with sine. This is 10 meters per second. Now let's decide our time interval for finding maximum height. Our time interval will be from the time the ball was kicked to the time of max height, which is right here. Here's a very important detail. At the peak of its height, the vertical velocity will be 0. It will only be traveling horizontally at that time for one very brief instant, and that's what we're going to find. There's an equation, and it's v y0 minus gt. We can rearrange this, and we'll get t equals v y0 over g. So there's our time equation that we're going to use. We plug everything in, 10 meters per second taken from here, and g is just 9.8. You get roughly 1.02 seconds. So there's our time value. So at 1.02 seconds, he's at his max height, the ball. Now let's find his vertical height or vertical displacement at this time. Let's use one of our original kinematic equations. Y equals v y0t minus 1 over 2 gt squared. Let's go ahead and substitute this for t. And you end up with y equals vyo times vyo over g minus 1 over 2 g times vyo squared over g squared. When you go and expand all this, which I'm not going to do because it's a lot of steps, you get this very important equation, which is also on the cheat sheet. It's y equals vyo squared divided by 2g. This is the formula for maximum height. Go and plug your things in. So 10 meters per second squared over 2 times gravity. This is roughly equal to 5.1 meters. There, done. That means this maximum height here is 5.1 meters. Now let's take the same situation but calculate the time it takes to return to the ground. So basically the whole trip. Our time interval would be t equals 0 seconds, so right here at the start, to the time he lands, which is what we're looking for. Now the initial height is equal to 0, and the ending height is also 0. So let's write out our equation. We're going to use this equation again, which is for displacement of y. Let's plug our values in. So remember, ending y is 0, starting y is 0, it's vy0t minus 1 over 2 gt squared. If you factor out t, you can actually get this equation here, which is t times 1 over 2 gt minus vy0 equals 0. This is a quadratic and there's two solutions if you use null factor law. The first solution is that t equals 0, which is correct, because here when y is 0, t is 0. The second solution is for the second y equals 0, which is what we're looking for. The second solution, when you rearrange it, is t equals 2v y0 over g. This is an important equation, and we're going to use it later on as well. Plug in our values, so 2 times 10 meters per second over 9.8, and it's roughly 2.04 seconds. So this entire trip for the ball took 2.04 seconds. I've made it a bit smaller because we need some space. Let me introduce to you a very important concept. It's called the level horizontal range. So the level horizontal range. The level horizontal range in this situation would be the total horizontal distance traveled. That is what it is. Now there's an equation for it. Let's call it R. The level horizontal range is R. And it has a formula, and it applies when a projectile lands at the same level that it started at. Now if this range is the total x distance, then we can say x is equal to R. And if you remember your kinematic equations, x is equal to velocity times time. Now let's substitute in for time that small formula that we found earlier. 2v y0 over g. This equals 2v x0 v y0 over g. And if you remember, this is equal to v cosine, and this is equal to v sine. So that means that it can be written as 2 initial velocity squared times sine times cosine. And remember, that comes from the formula for the x component and the y component. This divided by g. If you remember your trig, then you recognize this as an identity. So in the end, we can write it as r equals initial velocity squared times sine 2 over g. This is your formula. This is the important formula. And there's two variations, this and this. These are what you need to know. If you're going to write something down, you can skip all this, just make sure you have this down. Let's see this in action. Let's use it for our football example. So from our previous calculations, we know the total time this trip takes is 2.04 seconds. And the initial x velocity was 17.32 meters per second. So the level horizontal range, or the total horizontal distance traveled, is equal to this multiplied by this, which is roughly 35.33 meters. Here's the final example for today, and it's a pretty tricky one, but it's also really awesome. So you are a military engineer, and your task to design weapons. Right now you're making high-tech artillery, and it's designed, let's say it looks like this. It's like a cannon, okay? And it shoots a projectile at something 320 meters away. When something is fired out of this thing, it's fired at a fixed velocity of 60 meters a second. What is the best angle to fire this weapon at to make sure you hit this target? That's the question. Of course, ignore air resistance. Remember, our horizontal range formula is this. So let's draw a mini diagram. This is where we shoot our thing. This is where we want to end up. The distance in between is 320 and the starting velocity is 60 meters per second. We need to find the angle. This is a good start. We know the range is 320 meters. We also know the initial velocity is 60 meters per second. And g is of course 9.8 meters per second. And we're looking for the best angle. Now here's what we're going to do to find the angle. We're going to rearrange this formula for sine. And then we're going to plug everything in. So when you rearrange it for sine, you get sine 2 equals range times gravity over velocity squared. This is 320 times 9.8 divided by 60 meters per second. Use the inverse sine function and then divide by 2. And you find that the best angle to hit this target is roughly 29.92 degrees. Let's say you have two cars and your second car is going 50 kilometers faster than the first car. And he passes the first car like that. Then the speed of this car relative to the slower car is 50 kilometers an hour. Now this is relative velocity in one dimension along a line. It's very simple. And you can use simple arithmetic. But what if this car was moving this way and this car was moving this way? Then you can't just use adding and subtracting anymore. You have to use vector addition. Now I'll show you what that means and how you would use vector addition in relative velocity problems. Okay, imagine this is a river. And here's the water, right? Let's say the water is coming this way. Now imagine you have a little boat and you want to get across. Well, the vector we would use to represent the boat's speed without considering the current would just be this. So if there was no current, this is how the boat would move. But there is current. So let's draw the current in now. So the actual path the boat would take while being pushed by the water would be this vector right here. Now what I'm about to teach you is extremely important. You need to make sure you specify the reference frames correctly so you don't add and subtract the wrong velocities. Because as you most likely already understand, depending on the reference frame, your velocity is different. Like if you're standing on a train and you're walking around, your velocity relative to the train is different to your velocity relative to the ground. So let's go through a careful labeling process. We'll label this vector here as simply the velocity of the water relative to the shore, because it's moving relative to the shore. Now this vector here, we're going to label it as velocity of the boat relative to the water. And when you add them together, you get the actual path the boat will take. Now the actual path the boat takes is the velocity of the boat relative to the shore. So S. That's the basic concept of how you would use vector addition to find relative velocity. Now it's not just confined to two vectors. You can have as many as you want. Like if you had a fisherman walking on the boat, you could have another vector like this. Now before we move on to proper examples, there's something that's often useful to remember. And I'm going to write it in equation form first. So it's called the velocity of B relative to A is equal to the negative velocity of A relative to B. What does that mean? If A sees B and B is moving at 5 meters per second toward A, and A was moving 5 meters per second toward B, then A would see B moving at 5 meters per second, but B would see A moving at negative 5 meters per second. So I'll give you a real world example. Imagine you have a car again and you're speeding down the road. It's very nice scenery, right? And you have trees and you have buildings. The buildings see you moving at, a positive velocity, let's say 30 meters per second. However, you see the trees and buildings coming toward you at negative 30 meters per second. Does that make sense? Moving on to a proper problem now. So it's the same river situation, right? It's a river. Now your boat this time, in still water, so just the velocity of the boat relative to water, no current. The velocity, it moves at 8 meters per second. But the water is moving west at 4 meters per second. So that vector will look like this. What angle should you direct the boat at to counteract the stream and move in a straight line? Now remember, let's start with a careful labeling process. This here will be the velocity of the boat with respect to the water. This is the velocity of the water with respect to the shore, right? It's moving relative to the shore. This is actually a bit special. We're not meant to add the vectors here. It's a bit of a trick question, because if we went and added it, and your boat decides to go this way, you're actually helping the current. You want to push against it. So let's get rid of this water velocity, and let's move it here this time instead. Now we'll connect the vector like this, and that is what we're looking for. We're going to call it the velocity of the boat with respect to the shore. So the boat is supposed to go in the direction of VBS. Let's go and solve for the angle that we should travel at. Okay, I really quickly went and cleaned up how the diagram looks so that we can solve this problem efficiently. We're going to use Pythagoras to solve for this vector here, because as you can see, this forms a right angle triangle. Let's take our two vectors, so these guys, so that we can solve for the hypotenuse. VWS plus or squared plus VBW squared is equal to VBS squared. Substitute in our values and you get 4 squared plus 8 squared, which is 16 plus 64, which means that the velocity of the boat relative to the shore is equal to root 80. But that's not what we're looking for. We're looking for the angle. So let's go and use this value with trigonometry to find the angle that we need to drive our boat at. And we're going to use sine. You can use cosine if you want, but in this example, I'll use sine. So as you know, sine is opposite over hypotenuse. The opposite angle is 4 meters per second, because that's the speed of the water right here. The hypotenuse, as we just found out, is root 80. So root 80. Now take the inverse sine of this value, and you end up with roughly 26 degrees. So if you want your boat to look like it's going in a straight line, you want the perfect angle to drive your boat to counteract this water current, then you should launch it at 26 degrees. Now let me give you a new problem. Same situation, but let's say the river is 90 meters wide. How much time does it take to cross the river? And how far downstream do you get pushed? I'll walk you through this. Time is determined by two things: the distance of the river, which is 90 meters, and the velocity component in that direction. The velocity component in that direction is this vector VBW, which is 8 meters per second. Now, as you know, time is equal to distance over speed. So that means time is equal to 90 meters, the distance, over the velocity, which is 8 meters per second. This gives you 11.25 seconds. So that's how long it takes to cross the river. Now, how far downstream do you get pushed? Your displacement downstream is equal to the velocity of the water multiplied by the amount of time you're in the water. So the velocity of the water is 4 meters per second, and you're in the water for 11.25 seconds. This is equal to 45 meters, so you get pushed downstream 45 meters, assuming that you just go straight ahead.